In this video, we will look at a single-phase AC parallel RL and RLC circuits. All the formulas from before we can still use. The power triangle is also something we can use, and the current triangle. So this is new, and something called the inverse impedance triangle. Now you'll notice down here, this says for series circuits only, the impedance triangle. So although you can use the inverse impedance triangle, it is quite cumbersome to type into your calculator, a lot of steps, which could result in a mistake. So it's best to use either the power triangle or the current triangle. My preference is the power triangle. Once again, we can find our reactance using our reactance formula, inductive reactance and capacitive reactance. And for purely resistive circuits, our vectors are drawn on the zero axis. We have our voltage, current, and power in phase with each other. And our inductive circuits, purely inductive in this case, are generally lagging, or always lagging I should say, but we generally draw the arrow in a downward position. And our purely capacitive circuits, where our arrows are opposite of the inductive circuits, because they are 180 degrees out of phase, but there is no real standard. But a common use is up for capacitance, down for inductance. For a practical inductive AC circuit, in parallel, we have a resistive branch and an inductive branch with some resistance. Once again, we have a triangle rather than just a purely inductive circuit. And we can use the power triangle or the current triangle just for that portion of the circuit. Once again, preference given to the power triangle. So now we can try solve this circuit here. And once again, we do have a resistance and a reactance. Don't get trapped into using the impedance triangle. It won't work. The impedance triangle will, but it is tricky. Draw your vectors to indicate that we are actually adding vectors together, straight up for the inductance in this case. And like I said, it doesn't matter which way you draw them, as long as if you're mixing them up, that the capacitive reactance goes the opposite. It's in parallel, so we have equal voltage across each branch. And we can find our current by using Ohm's law. And realize that we are just adding vectors. 3 amps at 0 degrees plus 4 amps at 90 degrees will give us our circuit current. And we can use the current triangle to do that, which is 5 amps. One of the common mistakes a student might make in this circuit is adding these together. And the reason we can't add them straight up is because they aren't in phase. Here we get 5 amps, and then of course our overall impedance of 24 ohms. We could also have solved this using the power triangle, so we could have went directly to watts and VA and VARs. Here we're just having a look at what the inverse impedance triangle would look like. If we inversed 24, we would get 0.4167, and if we inversed 40, we'd get 0.025, and so on. Power factor, once again, the best way to describe it is watts over VA, but we could also use 3 over 5 in this case, or IZ over I circuit, IR I should say, over IZ, or the inverse impedance triangle works as well. And if you do the math, you will find that all of these triangles will have a power factor of 0.6. And once again, we can get the phase angle by inverse cos on our calculator to see that we're at 53.13 degrees. Now we could use the same method for a purely resistive capacitive circuit or an RC circuit. But now we'll look at a parallel circuit with a practical inductor. Once again, our power triangle and current triangle can be used. Parallel voltages. In this case, I'm going directly to watts and VA. Now, E squared over R will give you watts, I should say, and E squared over Z will give you VA. So that's important. We could find the current, 120 divided by 30, get 4 amps, and so on. Draw our vectors. Once again, our resistive vector is at the 0 axis, and now we have an impedance triangle or a power triangle or a current triangle for our inductive portion of the circuit. It does have some resistance that is in phase with this resistor. Put in your power values, watts here, VA here, transfer over your power factor, solve for watts, bars, and then combine the two. So 480 plus 172.8 gives us 652.8. Our VARs transfers down to this triangle, and we can solve for our overall VA for the circuit. Now the dotted line here is just giving you an indicator that that would be the inductive or practical inductive portion of the circuit. There's our VA. We can solve for the overall current for the system. Notice that they don't add straight up. 4 plus 2.4 would be 6.4. We have to add the current vectorially. And we could have used the current triangle to prove that, but in this case, we use power. Overall power factor, watts over VA, gives us 0.9430. And inverse cos to get the phase angle. Now you'll notice here that our arrow is pointing down, so we are in quadrant 4. So we could either write it as minus 19.44 degrees or 340.56 degrees based on clockwise from 0. Using the power factor of the coil, we can now solve for the inductive reactance for the coil. And here we can use the impedance triangle just for the inductor. Transfer the power factor, it'll be the same. Take our impedance, solve for our reactance using Pythagoras or a trig. And now we can solve for our inductance in henries using XL of 40. And our inductive reactance formula, transposing it to solve for L. In this case, we'll get 106, or I should say 0.106 henries, which we would normally write as 106 millihenries. Next up, we'll correct this same circuit to unity. So I just kept the vectors there as reference. Same values from the previous question, but now we have a capacitor in parallel. You can go with current or power. I went with power again. There's the current if needed. Solving for your watts and bars for this portion of the circuit. There's our original circuit as before. But when correcting to unity, all of the inductive bars will be cancelled out by the capacitor. So our arrow points up in this case. We're cancelling out our inductive bars with the exact same value, which is written up here. And we can now find our size of capacitor in microfarads using our XC equals 1 over 2 pi FC formula. Our voltage, because it's in parallel for the capacitor, will be the same. E squared over VARs will give us 62 ohms, or VARs divided by 120 will give us the current, and 120 divided by the current will give us 62.5 ohms, which we can then put into our formula to solve for our microfarads. If asked, you could also solve for your overall line current. And in this case, at unity, our VA is equal to our watts, so we'll use this value divided by 120 to get our line current, and of course 120 divided by 5.44 to get our overall impedance of the circuit. Well, once again, resonant frequency is involved with parallel circuits. And if you recall, resonant frequency is when capacitive reactance is equal to inductive reactance. And in series, we could have a super high current if we have a low resistance. In parallel, we will have a minimum current if it's still desirable. Of course, resonance is also known as unity. Our formulas from before to transpose and come up with the resonant frequency formula. And you might recall the bell curve from the series circuit was the opposite. We had a high rise in current as our resonant frequency canceled out the reactances and made them equal. But in parallel, since all the loads are seeing the same voltage, the current will be determined by the amount of branch circuit, not the frequency. And the change in frequency causes the line current to change to a minimum. So here we could be lagging and we change the frequency and go to unity, and then maybe if we kept changing the frequency, go more leading. And that's all.